Here is a second video that looks at L'Hopital's rule for finding limits of either one of these two indeterminate forms, 0 over 0 or infinity over infinity. And to remind ourselves how this works, let's go ahead and find the limit as x approaches 0 of 5x squared over 1 minus cosine x. Why is this a L'Hopital problem? Well, you kind of have to know you have the right form before you invoke L'Hopital's rules. Plug a 0 in here. You have 5 times 0 squared, which of course is 0. Plug a 0 down here. Cosine of 0 is 1, and 1 minus 1 is 0. So yes, you have 0 over 0, and that's one of the two forms that L'Hopital can help us with. L'Hopital's rule says replace the limit problem given to you with one that looks like this. Take the ratio of the derivatives of the original function. So what's the derivative of 5x squared? Of course, it's 10x. And the derivative of 1 is 0. And the derivative of negative cosine x is positive sine x. So you get something like this. And plug 0 back in. Now, on the top, the derivative of the expression 10x evaluates to 0. The sine of 0 is also 0. So we have a second application of L'Hopital coming. One more time, take a ratio of the derivatives of these functions. So the derivative of 10x is 10. The derivative of sine is cosine. Plugging in the 0 again, you can't plug it in on the top, but you can certainly put it on the bottom. Cosine of 0 is 1, so the form of the limit doesn't look like either one of these anymore, so we're in the clear, and we can just safely divide 10 by 1 and get an answer of 10. So I think this helps illustrate why this is called an indeterminate form. 0 divided by 0 in this problem came out to be 10. In some other problem, it might come out to be negative 12 or infinity, or 0. There's lots of possibilities. But that's a review of using L'Hopital's rule. Now let's take a look at this chart, which summarizes, I think, all the indeterminate and determinate forms I've ever seen. Here are two that are handled by L'Hopital. Here are a bunch that are not immediately handled by L'Hopital, but they might be. You might be able to take a problem where you see one of these indeterminate forms, and you might be able to manipulate the expression into a L'Hopital problem. That's coming up next when we do problem 2. And then we have determinate forms. So things you can count on. 0 or 1 or 10 divided by infinity is always going to be 0. Adding infinity makes infinity. Contrast that with this. Subtracting infinities might not make 0. Okay, 1 to the infinity power might not make 1. So some of these are sort of surprising, but if you get some experience with these problems, you'll be able to sort this out. So keep this chart handy, pause the video, copy it down, screenshot it, whatever you're going to do. Let's take a look at problem 2. When I first plug infinity into these expressions, okay, what does negative x squared look like? Yeah, that's an inverted parabola. Looks something like this. If x is going to go to infinity, where's y going to go? Negative infinity. So far, what do I know about this? I have negative infinity here. And what about 2 to the negative x? Okay, well that graph looks like this. Remember, 2 to the x is that exponential upward swooping function. 2 to the negative x is a reflection of that over the y-axis. So as x goes to infinity, where does the y go? It appears to be coming down towards 0. So what is infinity times 0? Is that 0? We grew up thinking multiplying with 0 always makes 0. But these are limits. The limits are weird. Okay, the idea is this is going towards 0. This is going towards infinity. This tries to make the answer very, very negative. And this tries to keep the answer close to 0 when we multiply. So this is not a L'Hopital form at all. But remember, 2 to the negative x is the same thing as 1 over 2 to the x. So probably the best way to tackle this problem is take the limit as x approaches infinity and rewrite this as a ratio that looks like negative x squared over 2 to the positive x, like that. Okay, now you have negative infinity up in the numerator as previously discussed, and this in the denominator this time goes to infinity. And so you have a L'Hopital form. And what does L'Hopital tell us to do? Take derivatives upstairs and down. Replace the limit problem with one that looks like this. Okay, we all know the derivative for x squared is 2x. You know the derivative of e to the x is e to the x. What about 2 to the x? The derivative turns out to be 2 to the x, kind of like e to the x, but you also have to multiply by the natural log of 2, and I'm not here to explain that today. We previously discussed what kind of limits these two have. It turns out these have the same limits as x goes to infinity. This linear function here goes to negative infinity. 2 to the x multiplied by some positive constant also goes to infinity. So it's the same form as in the last iteration. And we're going to apply L'Hopital's rule one more time. So we go like this. Take the derivative of negative 2x. Take the derivative of natural log 2 times 2 to the x. You got to keep this constant because it's multiplied. And then when you do the derivative for 2 to the x, you're going to get an expression that looks like this. So you'll have natural log of 2 times natural log of 2 times 2 to the x. It's kind of nice to write it like this. Okay, so what form do we have here? We have a constant, not 0, but negative 2. And on the bottom, when you plug in infinity, you get infinity. So what is negative 2 over infinity? That's right, it's 0. So we couldn't really know this in the beginning, but the question I asked was, what's going to dominate this product? The 0, which tries to keep the answer near 0, or the negative infinity? And in this case, the 0 was the winner. Okay, I want to do 2 more of these problems, and then I'm going to show you a way to do a problem like number 2 many, many times faster. It's called order of magnitude. We'll get there in just a second. Problem 3, take the limit as x goes to infinity of e to the x over x squared minus 4. Confirm for yourself that this has an infinity over infinity form, and it's appropriate to apply L'Hopital to that. Well, if you can take derivatives, you can do L'Hopital's rule. The derivative for e to the x is e to the x, and the derivative for x squared minus 4 is 2x. You will once again have an infinity over infinity form. So you're going to go ahead and apply derivatives one more time. Take the derivative of e to the x. Take the derivative of 2x. Evaluate with infinity, and this time we have this sort of a thing. Infinity divided by 2, which is still infinite. I was reading the other day that the L'Hopital's rule, named after Guillaume L'Hopital, probably was authored by somebody else like Johann Bernoulli. There's a little bit of a scandal behind this. Third problem. Natural log 3x over square root x. Take the limit as x goes to infinity of this ratio. Both of these go to infinity. They get there kind of slowly, though. But we have a L'Hopital form, so we're going to go ahead and apply derivatives again. The derivative of natural log 3x, of course, is 1 over 3x. But there's a chain rule factor of times 3. You cancel those 3's, and you'll find out that the appropriate derivative for the numerator is just like the derivative of natural log. It's 1 over x. And the derivative for square root x is 1 over 2 root x. Okay, you could try to find the form right now. It turns out it's 0 over 0. Or you could simplify this expression before you try to evaluate it. We might actually be close to done with this problem. Now, of course, 1 over x times 1 over, or divided by 1 over 2 root x is you invert the divisor, multiply by the reciprocal. You get 2 root x over x, but you can cancel square root of x and x, and that's going to leave you 2 over root x in the denominator. So let's go back up and make this substitution and take the limit as x approaches infinity of 2 over root x. This has the form 2 over infinity, which is, of course, 0, and that's the answer to problem 4. Now, if you need to pause the video in order to read this page, it talks about orders of magnitude for different functions. It says if you take the limit as x goes to infinity of a ratio of functions like this, okay, if the answer turns out to be 0, it's because even though both of these were getting big, the denominator, the divisor, was getting big much, much faster and overwhelmed the numerator, creating 0 for an answer. On the other hand, if you take the limit as x goes to infinity of a ratio like this, and let's suppose you get an infinite answer, either positive or negative infinity, that's because f of x was getting to either infinity or negative infinity much, much, much faster than g. There's a third possibility. You take the limit as x goes to infinity of this ratio, and the answer comes out to be a non-zero constant, like 2, or negative 4.5, whatever it is. In that case, we would say that these two functions have equal order of magnitude. Now, why do we fuss about this? Order of magnitude can help you solve certain problems that might require applying L'Hopital's rule once or twice. You might be able to solve these problems at a glance. We're going to go back and revisit problems 2, 3, and 4, and we're going to try to use this notion of order of magnitude to solve problems 2, 3, and 4 without all of the effort. Okay. Well, I got to find problem 2 here. Problem 2 looked like this. It was limit as x approaches infinity, and it was negative x squared times 2 to the negative x, which we promptly rewrote as limit as x approaches infinity of negative x squared over 2 to the x. All right, let's go up and look at this chart. X squared is said to be a power function. Power functions look like x to the k value, where k is any number bigger than 0. X squared, x cubed. This could even be x to the 0.5 power, you know, like the square root of x. That would be considered a function that goes to infinity at intermediate speed. It's got intermediate order of magnitude. This one does. Whereas 2 to the x is exponential. Any sort of b to the x function where the base b is larger than 1 gets to infinity faster than all others in this chart. So we don't have equal magnitudes here. The order of magnitude in the bottom is higher than that of the top. And so, according to what we just read, the answer is going to be 0. I think of it as, hey, this gets big. Or it gets negatively big. In absolute value, it gets big. It gets far from 0 pretty quickly. This gets there just much, much faster. So big divided by super big makes 0. Problem 3 we did a minute ago. I can see I applied L'Hopital's rule to it twice, but if you know this order of magnitude concept, you can get the answer in, I don't know, a fraction of a second. Here we have e to the x, one of my favorite functions, over x squared minus 4. Hey, both of these are going to positive infinity. Which one's getting there faster? E to the x. It's exponential. So you have a higher or highest order of magnitude over intermediate order of magnitude. This is going to go to either infinity or negative infinity, and I have no reason to think it's negative infinity. And last problem for this video, problem 4, we did a minute ago. It was limit as x goes to infinity and it was natural log of 3x over the square root of x. If you know this order of magnitude concept, this is a pretty easy problem to do in your head. We got an answer of 0 for it. Now, how could we have predicted that? Well, these don't have the same order of magnitude. Natural log, any kind of log, has got the lowest order of magnitude. In that chart above, square root of x is considered a power function. It has higher order of magnitude. So lower order divided by higher order. You know, both of these go to infinity pretty slowly, but this goes so much more slowly than that. And so the answer to this is 0. We have one more video coming where we take a look at some of the indeterminate forms I haven't really done much with yet. So we're going to have, infinity to the 0 power, 1 to the infinity power, quite a few 0 to the 0 power problems, and that's coming up in the next video, part 3. Hope you learned something. My name's Eric. Have a good day.